welcome back, and thanks for listening to episode 1 if you did, in this series called Driving Sustainability, the Role of Steel in the Automotive Industry. Let's now move on to episode 2, which is called Understanding Steel Grades and Traditional Steelmaking Processes.
Right, so you want me to talk about blast furnace steelmaking?
Alright, so let's pick this up here then, Bryan. How do we've already said in the introduction, but how do we go about making the steels that we've just been talking about at length?
Right, okay. Well, traditionally, steels for automotive have been made using the blast furnace basic oxygen steelmaking route, which was developed as the Linz-Donowitz process in the 1950s, and all the major steel companies worldwide then produced steels for automotive and packaging applications using that process. So in the blast furnace, you have two basic ingredients. You've got iron ore that's been processed through a sinter plant, which has modified the structure of the material and has reduced the amount of harmful impurities to some degree. And you've got coke. So coke originally is produced from coal. So typically from 34 tons of coal, you'll get 21 tons of coke. And that coke is the vital reducing agent, which reduces the sintered product, which consists of hematite, which is 2 atoms of iron to 3 atoms of oxygen, down to metallic iron. The end product of that process is that you release significant quantities of impurities, in particular oxygen, and end up with a product that contains about 4 to 5% of carbon present in it, which is the major impurity that's left in the iron product at the end of the blast furnace process. There are other impurities present as well, such as silicon and phosphorus, and that's where the Boss process comes into its own.
So going back to the blast furnace then, this is a big thing, isn't it?
Yes.
You know, it's a big tower that's got molten steel inside it.
Yes.
You know, we've walked past him.
Molten iron.
Molten iron, rather. I mean,
yeah.
You've worked in Tata for how long?
40 years.
40 years. You've seen the blast furnace a few times then?
Once or twice,
It's a big old thing.
Yeah.
How many have they got over there, or did they?
They've got 2 working blast furnaces in Port Talbot currently.
Okay, which pour out molten iron from the bottom.
Yeah.
After doing all of the chemistry in the middle.
That's right. So it's called hot metal at that stage because of the high levels of impurities that are present in it. As I said, 3 to 4% of carbon, for example.
And that's not good for us. We want to get down.
That's right.
To much lower levels.
That's right.
As we talked about earlier. We're talking what,
0.03 to 0.04% carbon.
Right. So there's a lot more to do then. Carry on, By.
So in the basic oxygen steelmaking process, there's a lot of sulfur present in coal. It's very difficult to avoid having sulfur in coal, and you have to pay a premium if you buy a low sulfur product. So what happens then is that in the first stage, before you pour the hot metal into the Boss vessel, is that there's a desulfurization stage. So in that stage, you reduce the sulfur down to levels which are appropriate then for a multi applications of sheet steel products. So following that desulfurization stage, you pour the hot metal into the Boss vessel. I put scrap in first.
What's Boss stand for, sorry?
That's a basic oxygen steelmaking.
Okay.
So you've got, say, 18-20% of scrap material. So you need less hot metal then to produce your product. So using recycled product, together with fluxes. And then during that Boss steelmaking process, there's a progressive reduction in the amount of elements that you do not require in your final product. Silicon is the first product to be taken out during the injection of oxygen, which is the primary means of producing steel.
So this is now, when I went to see it, this is a lance they actually put into the vessel. And this is a big vessel full of molten iron,
yes.
And then they put a an oxygen lance into it and blow oxygen through the
Yes,
through
so
the
you've got
melt.
300 to 400 tons of product in there, and the means of reduction then of the hot metal to steel is to use, as you said, oxygen injection. So that's injected at high speed into the vessel. So silicon is the most reactive element, so that's reduced first, and then you reduce the carbon that's present. So you're reducing the amount of carbon present by a factor of 100.
Wow.
And then phosphorus then is the last ingredient that's removed. You have to be careful that you don't inject the oxygen for too long, because what happens then is you start to convert the iron back to iron oxide, for example, which is the last thing you want. So typically the process will take, say, 18 to 20 minutes.
Okay.
So that then is poured out into ladles, are ready then for secondary steelmaking operations.
Okay, so we're on to secondary steelmaking operations then.
So from the blast furnace, you've got one product with, as I said, typically 3 or 4% carbon in it. And from the Boss steelmaking process, again, you've got one product, which is then has a much lower level of carbon and much lower level of other impurities such as silicon and phosphorus. And then you go to the secondary steelmaking, and this is now where you generate a much larger variety of products. So you change the chemistry then in the secondary steelmaking process. So by addition of various alloying elements, such as aluminium, titanium, and chromium, and so on.
Niobium.
And now you can end up with, say, 30 or 40 different chemical compositions. And then that moves then on to the rolling process. So you first of all cast the material into a slab, and then the material is processed through a hot mill, and then the processing conditions in the hot mill will vary very significantly depending upon the grade of steel that you want to produce. So you're now producing hundreds of different grades of steel dependent upon the processing characteristics that slab is subjected to during hot rolling operations. So,
and when you say the processing conditions, really what we're talking about with this kind of thing is heating and cooling, isn't it?
That's right.
And reduction of its gauge,
yes,
should we say?
So at the end of the hot rolling process, the hot roll coil progresses through a run-out table where water sprays are applied to it. The amount of water spray that's added varying very significantly dependent upon the product you're making. If you want to produce a relatively low strength ferrite perlite grade of steel, then what happens is that you will cool the hot roll coil down into what's called the ferrite nose, and then you'll stop the cooling to a certain degree, and you end up then with a microstructure that's a combination of low strength of ferrite together with a perlite microstructure. It's a combination of ferrite and iron carbide, Fe3C.
And they're your mild steels.
They're your mild
bog
steel
standard
products.
sort of mild steel products.
Yes.
Yeah.
If the second grade of steel that's generated in this on the run-out table is a ferrite bainite grade of steel. So in that case, again, you cool it down into the ferrite nose for a few seconds, and then you cool it more rapidly, and then you end up to produce a different product, which is this ferrite bainite grade of steel. And in this case, what the major change that takes place is that instead of having bands of ferrite and perlite where we have quite thick layers of perlite, by cooling it more rapidly, you end up with thinner layers of perlite in the microstructure, far more layers of them, and as a consequence of that, you're strengthening the steel to a significant degree compared to a ferrite perlite grade of steel.
Oh, brilliant. Brilliant bits of technology here.
Yeah.
Okay.
And then the third sort of primary cooling program that's adopted is to produce the dual phase steel. So in this case, again, you're cooling down to the ferrite nose. You'll always need ferrite for formability. So you'll
That's the soft stuff.
That's the soft stuff, yeah. So you're cooling it down into the ferrite nose, hold it there for a limited period of time until you've got as much ferrite as you want, and then you quench it. And when you quench that product, you end up with a microstructure that's far more disorganized, far more regular in shape. A martensite microstructure, which, as I mentioned earlier, is a very hard grade of material, which imparts significant strengthening to the product. So then, when you use this product in an automotive architecture, what you've got is the ferrite is giving you the ability to form parts to a certain degree, and the martensite then strengthens that product to enhance the crash resistance, for example, of the product. And as I mentioned earlier, the more martensite that's present, the higher the strength, but the more limited is the formability of the product.
Brilliant. So we've got that covered then. We're on, where are we now, Bryan, in the process?
You're now making sort of potentially thousands of different grades of steel.
Okay. So that's the run-out table. What happens after that?
Well, then most of that steel is sold as a hot roll product. But then there's a more limited amount of cold roll products required in the marketplace. So if you're making radiators, if you're making automotive grades of steel for automotive body and white construction, then you want a cold rolled steel. So the cold rolled steels then have advantages compared to hot rolled steels in terms of better finishing. So the surface finish on these products is significantly better, as well as you're generating then a wider range of products again, and satisfying the requirements of automotive construction in particular. Whereas for the chassis applications, for example, then it's hot roll products then that are used predominantly worldwide.
So we won't go into it too much then, but we mentioned now there's two types of rolling processes. There's a hot rolling process and there's a cold rolling process.
That's right, yes.
Hot rolling comes first.
Yes.
Cold rolling comes after that, and they'll produce very different products from each.
Yes.
And we will depend on the application.
Yes.
That,
and typically for hot roll steels, you're looking at thicknesses varying from, say, 2 millimeters thick, maybe even a bit less than that, up to, say, 17 millimeters thick at Port Talbot. So depending on what's required, if you're looking at heavy construction manufacture, bridges, buildings and what have you, then you're looking at much thicker grades of steel.
Okay. So we've got a cold roll product. There's hundreds of these, thousands of these probably,
yes,
is there?
That's right, yes.
Some of them for automotive, some of them for not.
Some of them, yeah.
Okay.
Yeah, and some of these grades then of hot roll steel, for example, will progress to a coating line. So if we take Trostre, for example, which is based in Llanelli, then they take a hot roll product, say 3 millimeters thick roughly, and they will reduce that in thickness by a factor of 100 for many grades of tin plate products. So there's a cold mill then in Trostre, which is used to reduce the thickness to the final thickness required for tin plate products, which are then coated primarily with tin. There's a limited amount of chromium coating as well, or polymer laminate coatings for those products.
Yeah, that's for the packaging industry, isn't it?
That's right, yes.
Okay, so let's focus. Let's go back to the steel industry.
Right,
sorry, not the steel industry. The
automotive,
automotive industry.
Yeah, the final point I should mention there is that whereas traditionally back in the 1950s, uncoated mild steel was used in the body and white structure, there were major problems with rust associated with that product, as I remember from some of the vehicles I bought in the 70s. And there was a gradual transformation to the use of coated steels then. So you're talking about a thin coating of zinc, either pure zinc or an iron zinc alloy coating, depending on the automotive manufacturer's choice. And that then has led to a massive increase in the corrosion resistance of a body and white structure. So it's rare these days to see a modern car, that's got any rust on it.
You should see mine. Okay, corrosion and coatings, that's another huge topic.
So automotive these days is all coated.
Yeah, of course.
For the body and white, uncoated then for chassis, and that then is powder coated to achieve high levels of corrosion resistance in the chassis and suspension market.
Yeah, okay. Right then, so that's a brief overview then of the basic oxygen steelmaking process.
Yes.
Blast furnace. What about the other type that we mentioned already?
Electric arc furnace route.
Electric arc furnace route. Now,
Yes.
how does that differ?
Well, with the electric arc furnace route, you've got, first thing, it consists of two sections. You've got the main body of the furnace itself, which is refractory lines, got outer steel casing, so refractories there are there to protect the steel casing. And then you've got a roof section. So you take the roof off, you input your scrap material, and you then have 3 electrodes if it's an AC process, 1 electrode if it's a DC process, and those are then enter through the roof of the furnace. You then melt the steel, and you add things such as flux, for example, then which aids in removal of some of the impurities that are present. So you get a slag film then developed on the outer surface of the molten steel in the furnace. You also use carbon and oxygen injection, which again is beneficial in removing impurities. There's a fair number of emissions generated in the process, and those are captured and are used then, the very high temperature, so they can then be used to preheat the scrap prior to sort of application to the furnace, and in that way you're saving on electricity cost because the steel then is at a much higher temperature. So you then get your slag layer, and after a certain period of time, you then empty the slag out of the furnace to begin with, and then you pour the molten steel out.
Okay, so now in this case, then we're using a purely electricity to melt our steel. A very high temperature.
Yes.
We're talking like over 2,000 degrees.
2,000, 3,000 degrees centigrade, yeah.
And now we've got we've come to the same place almost, haven't we? We've got, except we've not used an iron ore. We're using scrap material.
Yes.
Melting it, and now we've got a molten metal.
Yes.
And we've tried to reduce the impurities in it by the methods that you've just mentioned there.
Yeah. I mean, the other aspect just to mention, because the focus is mainly on automotive, is that product may not be suitable for automotive applications, because if you talk about the main grade of scrap steel that's available, then typically 75% of the steel is classed as merchant scrap. And in merchant scrap, there's no control in the chemistry, basically. So the biggest element of merchant scrap is reinforcing bar, for example. So that contains a lot of tramp elements, such as copper and tin, nitrogen, and other elements which are deleterious if you're making a highly formable grade of steel. The other types of scrap available, though, are process scrap, and this is steel which is generated from the rolling processes in particular, where, for example, the ends of a slab haven't got the right shape, so these are cut off. So you've got a nice square slab that's fed through to the hot rolling process. And customers, for example, will order varying widths of steel. So a standard, Port Talbot, you say you'll have something that's 1800 millimeters wide, but a customer may want something that's 1500 millimeters wide. So you have to use edging equipment to cut off the excess material. Other customers, for example, may require something that's only 700 millimeters wide. So then you have to go to a stockist. So a stockist would receive material that's 1800 millimeters wide, and may then supply the end customer who wants, say, a limited quantity of steel with material that's 500, 600 millimeters wide.
So there's a hierarchy then of scrap, basically, is what you're saying, isn't there?
Yes.
Some scrap is better than other scrap.
That's right.
So the scrap from the offcuts of the materials that we know about,
yes,
are higher grade.
And the final sort of grade of scrap that's available is that from, say, automotive manufacture. So typically, you put a ton of steel into an automotive factory, and half of that ends up at scrap at the end of the day. And that is then scrap of known composition. So you'll have different bins of scrap for, say, high-strength steel or a dual-phase steel. And that can be sold then back to a scrap merchant who can demand a much higher price for the product because it's of known chemical composition. So that sort of product would be ideal for automotive. Unfortunately, as I mentioned, 3/4 of the scrap available worldwide is merchant scrap. where there's limited knowledge on its chemical composition. So the only way around that then is that if you're making, say, a steel for an automotive application, then maybe you'd only use process scrap or end-of-life vehicle scrap from a car plant, say, for example. So when a car comes to the end of its life, if you can sort out those materials into different bunkers in a shredding plant, then you know the composition of those grades of steel. So as well as the offcuts from the automotive manufacturer itself, you've also got then the potential for having sorted out scrap from a shredder. Unfortunately, there aren't many shredders that have that capacity to sort out the steel into different grades of material. So the consequence of that then is you either either sort out your scrap. So if you're making a particularly challenging chemical composition, you'd use scrap steel of known composition only. Or alternatively, a product that we haven't discussed as yet is direct reduced iron, which again has a known chemical composition.
Tell me about that then, Bryan. That sounds great. So, I mean, so far, from what I've understood off you, is that it's not ideal to mix steel using the electric arc furnace method.
Not for not for many strip steel applications. There would be some, but if you're talking about the automotive industry in particular, then you want a grade of steel that's got a specific chemical composition to meet the attributes of formability and strength required in automotive in vehicles on the road. So
I guess, as you were saying earlier, we can get that from the basic oxygen process.
You can,
and it's
yes.
a little bit more challenging, a lot more challenging in the
electric arc furnace.
And you were mentioning then going on to talk about how we might do that using this.
Yes.
DRI process.
This DRI product, I mean, so the DRI product then is of known chemical composition. There are two main processes for producing DRI. There's the natural gas process, which accounts for, such as the Midrex process, which accounts for about 78% of DRI production, and there's the Corex process, which is the next process that's widely used, which is a coal-based process. So in the natural gas based process, you're basically using natural gas, mixing it with steam to generate carbon monoxide and hydrogen, and those are then used to use your iron ore product down to a metallic iron at the end of this process. So it involves a shaft furnace, so you feed in your iron ore at the top of the furnace, and then mid-furnace you apply carbon monoxide and hydrogen then as a reducing agent to reduce that iron ore, firstly from hematite, which has got 2 atoms of iron to 3 atoms of oxygen, to magnetite, which has got 3 atoms of iron and 4 atoms of oxygen, then to wustite, we've got 1 atom of iron to 1 atom of oxygen. So you're progressively reducing the relative proportion of oxygen in that ore material, and then finally you end up with an iron product, which contains quite significant amounts of impurities, but nevertheless you've got a controlled chemistry.
Which is important.
Yeah. The Corex process is different. You're using coal, and it's got 2 elements to it. So you've got your shaft furnace and then a bottom reducing furnace. So from the reducing furnace, you generate carbon monoxide by injecting oxygen, as in the Boss process, and carbon. So you've got carbon converted to carbon monoxide, which is then transferred from the reducing furnace to the shaft furnace above it to act as the reducing agent. So that produces quite significant levels of carbon, so you're talking about 4% of carbon or more, together with a significant level of impurities. So these DRI reduction processes convert an iron ore to a usable product for the electric arc furnace, but nevertheless, the level of impurities is significantly greater than from the Boss process.
Oh dear, still.
Yeah, still. So this is where you move on now to the secondary steel making process, which has particular significance then, I should say, in the generating of a product for which are appropriate for say automotive applications. So you've got the RH Reinstahl process, which is a vacuum degassing process, which can reduce the carbon level down to carbon and nitrogen level down to 0.003% carbon and nitrogen. So that's suitable as an interstitial free steel, which is used in automotive assembly, where you've got particularly challenging applications in terms of formability. Strength is more limited, of course, because you've now achieved this high level of formability, but you have to accept the fact that for certain applications in a body structure, you've got a highly complex geometry, and you ain't going to use a dual phase steel for that.
No.
You've got to have a lower strength product to achieve then the performance you require. Bake hardening steels then, of course, come into their own, where you've got very good formability, not as good as, say, an interstitial free steel.
Yeah, and we talked about bake hardening steels already, haven't we?
Yes. So the other sort of process is CASOB, compositionally adjusted argon and oxygen blowing. And so that's a process that's widely used for Bosch steelmaking operations for the production of many of the sort of run-of-the-mill products, radiators, shelving, and what have you. A lower cost process than the Reinstahl vacuum degassing process, obviously.
Okay then, Bryan, so we've got these processes. We've got our blast furnace and basic oxygen processes, and we've got now the electric arc furnace along with the other two processes that you've just mentioned.
Yes.
So we're still in a position, no matter what process you use, we're going to be producing carbon dioxide.
Yes.
So I mentioned earlier about the numbers.
Yes.
And we said, what was it, about 1.8 tonnes?
It's 1.8 tonnes of carbon dioxide to 1 tonne of steel, predominantly as a consequence of blast furnace operations. So that's 90% of the carbon dioxide emissions from the blast furnace basic oxygen steelmaking route.
And then now it gets a bit more complicated for the second one, doesn't it?
Yes.
Because it's the electric arc furnace. You could either use the simple method of producing steels for reinforcement bars, as we say.
Yes.
And then that will have a lower...
that will have lower levels of carbon dioxide emissions, down to 0.4 tonnes of carbon dioxide emissions for 1 tonne of steel, producing long products, basically.
Now, if we want to produce automotive products from that method, we're talking...
The use of scrap steel, potentially, which has been sorted out much more efficiently, which has got lower levels of tramp elements such as copper and tin and nitrogen, and other elements, too much chromium or molybdenum, for example, as tramp elements as well. So you're starting off with a chemistry in the scrap, which is better, also combining that with DRI, so you know exactly what the composition of that is, and you're able then, via the electric arc furnace route, via slag formation, for example, via the addition of carbon and oxygen to the electric arc furnace process, which is a dual purpose. You're getting much more efficient mixing of the steel. There's a foam developed as a consequence of the generation of carbon monoxide during the process, which provides a significant amount of heat for the electric arc furnace, as well as generating higher levels of impurities from the melt. You've then got a secondary process where the carbon monoxide oxidizes to carbon dioxide, which generates 4 times as much energy as the carbon to carbon monoxide process. So you're now generating a lot of heat in that furnace, and it has this beneficial effect, as I said, of reducing the amount of electricity that you require, and also getting rid of far more impurities in the material.
But we still producing carbon dioxide from that process, aren't we?
That's right.
Which is unavoidable. And so, what does that raise our per tonne level to then? Should we say
it could be up to a 1 or even 1.4, I think it was, were the figures that you showed me this morning, for example.
Okay, yeah, okay. So we don't need to know exact figures,
No,
but
they're lower levels.
They're lower levels, should we say?
Yes.
Yeah. Okay, then that's okay. So
and you've now got a product which is more appropriate for strip applications.
Okay. So my next question is, Bryan, can we produce all the grades of steel that we need for automotive applications from the electric arc furnace?
Well, that's an open question from what I can see.
Fantastic.
Because the literature tends to suggest that there are limitations in terms of getting the right chemical composition if, for example, you're making interstitial free steel for packaging or for automotive application. So this is a sort of work in progress, if you like. So because of the cost advantage of making strip steels via the electric arc furnace route, because you're using less energy in converting scrap to steel than in converting iron ore to steel, then there's a cost benefit there. But there's also then, as I said, this premium market in automotive and in certain packaging grades. If you can get the right chemical composition to achieve deep drawing cans, for example, as we know from our joint lecture on tin plate. So
the packaging industry, would you say it's more promising than the automotive industry at the moment?
But there are these challenges in getting the composition, and to be honest, I don't know how far that has progressed.
Oh, that's fine. Yeah. Well, that's something.
And then in the long term, for net zero carbon 2050, people are talking about the use of the hybrid processor, for example, which uses hydrogen rather than carbon for reducing steel.
Well, that's going to be the subject of our next talk, isn't it?
Yes.
Fossil-free steels.
Yes, that's right. Yes.
Yeah. Right. Well, thank you, Bryan.
Well, can I just add one comment?
Well, I was gonna say to you, is that all we need to talk about? But no, it's not.
I mean, the estimate is that by 2050, there could be as much as 15% of steel generated using hydrogen as the reduction source, which still means that 85% is being produced because of the legacy of plant, in that most of the production in steel is by the blast furnace boss making steel route. People have invested in that plant. They're not going to close down all that plant to convert to electric arc furnaces or to the hybrid process for the manufacture of steel. So there are different trends in different parts of the world. So in America, for example, there's more steel produced by the electric arc furnace route than by the blast furnace boss route. If you take companies such as Arcelor, then in Europe, they are receiving a very large subsidy from the French government to close down some of their older blast furnaces and build a new couple of electric arc furnaces in Dunkirk, in France. So they are transitioning from a sort of high carbon dioxide emission product portfolio which they have to sell, to one where the amount of carbon in the product is going to reduce significantly by the time these electric arc furnaces come online by about 2030, I think it is, or even sooner than that.
Okay, that's interesting, Bryan. Now, is there anything else you want to add now to this before we finish?
That's it for the time being.
That's it for the time being. All right, well, hopefully that's given us an overview of the types of chemistries, the types of properties we need for steel. I'm going to say that again. So hopefully that's given us a good overview of what's required in terms of steel to make a vehicle. Yeah. Okay, there's not, we're not going to differentiate too much between an electric vehicle and a normal ICE vehicle right now, aren't we? No. They're basically one of the same right now, aren't they?
That's right. And the steels that you developed for the battery electric vehicle would be the same as for a hybrid vehicle, for example, or a conventional petrol vehicle until petrol is phased out, whenever that's going to be phased out. I mean, if you look at the UK, for example, the plan is that by 2035 now, there'll be no new car can be sold which is a petrol car or a diesel car.
Yeah.
So that's the plan.
That's the plan. Okay. And then we've looked at the couple of different methods of how to make that steel, that said steel.
Yes.
We've talked about how that they produce carbon dioxide, which is a problem.
Yeah.
And so, you know, there's something there, isn't there? And what's the embodied sort of carbon dioxide content in a new car?
Yes, that's right.
Type thing, which we haven't really discussed, and we're not going to either, because that's just figures on a piece of paper, isn't it?
Right.
We can go and do a Google search on that.
Yeah.
It's just sort of, this is going to give you an appreciation of the work that really has gone into making these products. And also then, an introduction to our next topic, which is making fossil-free steel.
Yeah.
Yeah. And that's it. Thanks for listening.
Right, okay, so we'll have lunch now.
There you are. Cheers, Bryan. Ta-ra.